Welcome. In this video, we will distinguish variables and values of variables, build tally plots and FDTs for quantitative data, and introduce frequency polygons. When working with qualitative data, we saw that the FDT, the frequency distribution table, was a convenient way to summarize the data. In particular, we could represent the data in a much smaller space. We also saw that protocharts and frequency bar graphs allowed us to visually display which values showed up more frequently or less frequently in the data set. Again, the purpose was 1, to make the data take up less space, and 2, to show relative frequencies for different values of the qualitative variable measured with our data. We will now extend these very concepts, the FDT and the frequency bar graph, to quantitative data, but we will add one more objective to our process. We also want to see the quote-unquote shape of the data. Unlike with qualitative data, the shape of the data is meaningful for quantitative data because we can ask questions like, is there more data at one or the other end of the range of the data set? Is there more data in the center range of the data or in the extremes? Or, is there a uniform consistency where each range of values is equally represented, or do some ranges in the data set have more values than others? All of these questions are questions about the shape of the data set. This will become clearer shortly. First, as a reminder, we need to move beyond ordinal data, and by extension nominal data, for this type of an exploration. This is because we need to be able to both order the data and have a consistent metric for the distance between the values of the variable being measured, i.e. we need interval or ratio level data. For example, if we have a 20-point quiz where a point is earned for each question correctly answered, then the gap between the scores of 9 and 12 is the same as the gap between the scores of 15 and 18, namely a difference of 3 more points. Recall, with ordinal data, this is not necessarily the case. For example, using the Likert scale, the size of the gap between disagree and neutral may be very different than the size of the gap between agree and strongly agree. For quantitative data, the fact that we have this consistent metric for the differences between values means that the data can be placed along a number line, and the corresponding distances between different data points tells us something about how far apart those values truly are. Let's revisit some vocabulary. In particular, we need to reiterate the difference between variables and values. Using a nominal example, eye color is a variable, and blue, brown, green, hazel are some of the possible values of the variable eye color. Using an ordinal example, response on a Likert scale is a variable, and strongly disagree, disagree, neutral, agree, strongly agree are the values of the variable response. At this time, we are working with data sets with only one variable. These are called univariate data sets. It is possible for data sets to have more than one variable, and we will explore these types of data sets later in the course. But for now, we will focus on one variable. However, the key is that while there is only one variable measured, there are many values observed for that variable. One value for each unit of analysis. For example, for each person responding to a survey, for each bear weighed in a study, or for each increase in performance for participants in an experiment. The key is that the data set will most likely contain many values for the variable, but only one variable is being measured. And it may be the case that some of the values in the data appear more than once. For example, different people have the same scores. Again, to emphasize the point for a univariate data set, the data consists of one variable. While many values of that variable are observed in the data set, they are all values for the same variable. Sometimes the word factor is used in place of variable, say temperature, and the term levels is used in place of values. In particular, the levels are the different values the factor might assume. For example, different temperature settings for the room in which students are asked to sit an exam. So, values are to variables as levels are to factors. Why is this distinction important with quantitative data? Well, there are two reasons. The first is general to data, and the second is specific to quantitative data. In general, we are interested in summarizing the frequency with which a value, or range of values, appears in a data set. Thus, it is important to distinguish the values from the variable being measured, and in turn to distinguish the data values from their frequencies. There will be more on this shortly. This is true for any type of data. But for quantitative data, we need to think about all of the possible values that might be observed for the variable being measured in our data set. For example, for nominal data, an FDT only needs to show the values observed. That is to say, the FDT would conventionally only have rows for the values actually observed. Using our eye color example, we observed blue, brown, hazel, and green eyes. Thus, there would only be these 4 values in the frequency distribution table. We could include a row for purple, as people can have purple eyes, though this is very rare, and as no one in our data had purple eyes, the frequency count for that value would be 0. Again, the convention is not to include values that have 0 frequency, unless one key aspect of the story you want to tell with your data is that none of that particular value was observed. Otherwise, it is just a waste of space, if you will. For ordinal data, it may be required to include classes with 0 frequency, but not always. For example, with the Likert scale, if you only observe neutral, agree, and strongly agree responses, it is perfectly acceptable to construct an FDT with only those 3 values reported, though you still would want to report them in the correct order. If there is a value missing in the ordinal scale, you get to decide if you wish to include it in your FDT or not. For example, if you only have disagree, agree, and strongly agree responses, no neutral or strongly disagree responses, some might want to include the neutral, with a frequency of 0, in the table just to emphasize the quote-unquote distance between agree and disagree. But there would be no issue in not including it. This is not how it works for quantitative data. The general rule with quantitative data is that you would indeed show all the possible values for the variable ranging from the minimum observed in your data set to the maximum observed. For example, let's say we have data on a 10-point quiz, and the lowest score was a 5 and the highest score was a 10. 1 point for each correct answer. If you had scores of 5, 6, 8, 9, and 10, but no scores of 7, you would not omit the value 7 from the FDT, or from any corresponding plot. This is because there is a meaningful gap between the observed scores of 6 and 8, and the table and/or graph helps convey this. Let's look at how tally plots show the shape of the data, and this point will become clearer. The construction of a tally plot for quantitative data is very similar as for qualitative data in many ways. Each time we encounter a particular value in the data set, we will put a tally mark next to that value in the plot. The one main distinction is that we start the tally plot by listing all of the possible values between the minimum and maximum values of our data set. You may recall, with nominal data, we add a new row to the tally table each time a new value for the variable appears. Then, once we have tallied all the data, we can choose to rearrange the tally plot by increasing or decreasing frequency, or by any other order we might prefer. Quick comment, either strategy could actually be used for ordinal data. The first thing we will do is note and record the minimum value in the data set. This is where the tally plot will start. You can confirm that for this data set, the minimum value is 5. Next, we will note and record the maximum value in the data set. Here, that value is 10. Before we begin to mark a tally for each time a value appears, we will fill in the possible values between our minimum and maximum, namely the values 6, 7, 8, and 9. Next, we will build the tally plot by placing a mark, or tally, next to the value as we observe it in the data set. 8 is the first value, and we will check it off as we mark it in the tally plot. Next, we have a 9, and another 9. Continuing, 9, 7, 8, 9, 8, 5, 10, 7, 8, 8, 7, 8, and that is all of the data. Note, there were no values of 6 in the data set, i.e. no student scored a 6 on this quiz. However, we still include an empty row for 6 in the tally plot to emphasize the shape of the data. In this case, we can see that most of the values were 7, 8, and 9, and there was 1, 10, and 1, 5. But the 5 is further below the majority of the data than 10 is above the majority of the data. This is what we mean when we talk about the shape of the distribution of the data. You may note that the mark used for the tally plot here was a dot instead of a traditional tally hash, a short vertical line. For rather obvious reasons, this version of a tally plot is called a dot plot. Here's what the tally plot would look like if we had used tally marks instead. This form may be familiar to you, and you may have been taught to cross a bundle of 4 tally marks with a diagonal fifth tally mark. This is often called the picket fence or 4x5 hash plot. In general, statisticians do not prefer this version of a tally plot because it obscures the shape of the data. You may have noticed that the length of the tallies for 8 got just a bit smaller in the picket fence plot. This makes it slightly more challenging to make comparisons for the frequency of one value to the frequency of another value. In particular, in the picket fence plot, it looks as though the frequencies for 8 and 9 are closer than they actually are. Though not shown here, I once encountered an interesting variation of the picket fence plot. I call it the dot box X plot. It is a similar type of counting by grouping approach, but instead of chunks of 5, 4 lines crossed by a fifth, you count by groups of 10. The first 4 marks are the dots of a square, the next 4 marks are each of the sides of the square, and the last 2 marks are the 2 diagonals of the square. So every fully crossed square indicates a group of 10. The same issue of obscuring the shape would hold for such a plot, but it does provide a relatively painless way to get a tally for a large set of data if you don't have easy access to technology. In general, tally plots are most often shown vertically, whereas dot plots can be drawn horizontally or vertically. A key difference for a dot plot is that it assumes you have a scale, and the scale can be indicated by tick marks along the axis. Note, unlike the tally plot, the dot plot does not require the data to be discrete, as we have here, but there will be more on the distinction between discrete and continuous data later in the course. There is another variation of the dot plot along an axis, and it is called a rug plot, which despite its name can be presented horizontally or vertically, but we will wait to introduce this until we talk about data sets with more than one variable. As with qualitative data, we can easily convert the tally plot to an FDT, a frequency distribution table. That is, we will convert the visual plot to a summary table. In the first column, we indicate the values of our variable, including the skipped values, just as we see in the tally plot. Now, in the second column, we indicate the frequency of how often each value was observed. Again, for a plot or table such as this, we do indeed want to include the unobserved values that would naturally appear in the sequence, and we will appropriately indicate the frequency for missing values as 0. Before we go on, let's revisit the idea of variables and values. The variable here is the quiz score. The variable is not frequency. And the values we observed were 5 through 10. Well, not 6 technically, but our observed values were between 5 and 10. Note, the data are the values. The data are not the frequencies. The frequencies just indicate how often that value showed up in the actual data set. More specifically, the data are not 1, 3, 6, 4, 1. The data values are 5, 7, 8, 9, 10. And we would have to repeat those values using the frequencies to get the complete list of the actual values. A minor distinction, but the first column in the summary table does not contain the data. The first column contains the values of the variable in the range of our data. Finally, let's introduce the frequency polygon. The frequency polygon is a graphical representation of the FDT that more specifically allows us to focus on the shape of the distribution of the data. Thus, we will need to use the FDT to draw the frequency polygon. Starting with the FDT, we will indicate the quiz score along the horizontal axis. For the frequency polygon, the frequencies are plotted along the vertical axis. Now we will draw a point at a height indicating the observed frequency. Here we plotted the point 5, 1 for the score of 5, which was observed in the data set only once. We continue with the rest of the values. 6, 0, 7, 3, 8, 6, 9, 4, 10, 1. And we have points for all of the frequencies, including the 0 frequency values in the range of our data. Next, we connect the points, and we almost have a complete frequency polygon. As we have drawn it here, conventionally, this plot would be considered incomplete. This is because the convention for a frequency polygon graph is that the polygonal path should start and end on the horizontal axis. The purpose for this convention is that it serves to emphasize that our lowest observed value was indeed a 5 and the highest observed value was a 10. The way we achieve this is that we always start and stop on the horizontal axis. We will start on the horizontal axis at the value just below our minimum value, and we will end on the horizontal axis at the value just above our maximum value. This makes it look like the plot starts and stops at 4 and 11, which it does, but the meaning here is that 4 is the largest value below the minimum that was not observed, thus it has a frequency of 0, and consequently the minimum for our data value was 5. Likewise, 11 is the smallest value above our maximum value that was not observed, i.e. has a frequency of 0. So the maximum is 10. From the plot, it is understood that all the frequencies above 11 and below 4 would be 0, and if you follow convention, there is no need to indicate this further, though it doesn't hurt to draw the horizontal lines on the axis, if you wish. Thank you for your attention. I hope this brief demonstration was helpful to you.